Welcome back to our physiology class. From the previous Special Forces journey of red blood cells, we know that the primary mission of red blood cells is to transport oxygen. 98.5% of oxygen transport in the body is carried out by red blood cells. Red blood cells rely on the hemoglobin molecules within them to carry oxygen. Due to the unique structure of hemoglobin, the binding and dissociation of oxygen with hemoglobin exhibit a characteristic curve. This is the oxygen dissociation curve we are going to study today. The oxygen dissociation curve is a graph showing the relationship between the partial pressure of oxygen, PO2, in the blood and the oxygen saturation of hemoglobin. It is also called the oxyhemoglobin dissociation curve. This curve shows both the dissociation of oxygen from hemoglobin at different PO2 levels and reflects the binding of oxygen to hemoglobin at different PO2 levels. Before explaining the oxygen dissociation curve, let's first look at what the horizontal and vertical axes on the graph represent. The horizontal axis represents the partial pressure of oxygen, PO2. The vertical axis represents oxygen saturation. What is the partial pressure of oxygen? Let's first understand what partial pressure of a gas is. The partial pressure of a gas refers to the pressure that a specific component of a gas mixture would exert if it alone occupied the same volume as the mixture at the same temperature. It can be simply understood as indicating the concentration or amount of a specific gas in a gas mixture. Therefore, the greater the partial pressure difference of a gas, the higher the concentration of that gas molecule. The partial pressure of oxygen indicates the concentration or amount of oxygen. Hemoglobin oxygen saturation refers to the extent to which hemoglobin is bound with oxygen, i.e., the percentage of oxygenated hemoglobin to total hemoglobin, or the ratio of hemoglobin-oxygen capacity to oxygen content. Simply put, if we assume one red blood cell contains only one hemoglobin molecule, and if you have a total of 100 red blood cells in your body, could they carry 400 oxygen molecules? This is the maximum oxygen carrying capacity of your red blood cells, called the oxygen capacity. But in reality, not all hemoglobin in red blood cells binds with oxygen molecules. Actually, perhaps only 388 oxygen molecules bind with hemoglobin. This is called the oxygen content. At this point, the oxygen saturation is 388 divided by 400, which equals 97%. Since the partial pressure of a gas is the driving force for gas exchange, physiologists wanted to see, under different PO2 levels, whether hemoglobin tends to release oxygen molecules or bind with them. Thus, the oxygen dissociation curve was established. The oxygen dissociation curve appears as an S-shaped, sigmoid, curve on the graph. Based on the S-shaped trend and functional significance of the oxygen dissociation curve, we artificially divide the curve into three segments. The first segment is the upper part of the curve, i.e., the right portion, corresponding to hemoglobin oxygen saturation when PO2 is between 60 and 100 millimeters of mercury. Its characteristic is that it is relatively flat, indicating that within this range, changes in PO2 have little effect on hemoglobin oxygen saturation or blood oxygen content. When PO2 is 100 millimeters of mercury, equivalent to arterial PO2, hemoglobin oxygen saturation is 97.4%, and the oxygen content is about 19.4 milliliters of oxygen per 100 milliliters of blood. Even in high altitudes, at high elevations, or in patients with certain pulmonary ventilation or gas exchange disorders, where the inspired oxygen partial pressure decreases, as long as the arterial PO2 does not fall below 60 millimeters of mercury, hemoglobin oxygen saturation can still remain above 90%, and the blood can still carry a sufficient amount of oxygen, preventing significant hypoxemia. The second segment is the middle part of the oxygen dissociation curve, corresponding to hemoglobin oxygen saturation when PO2 is between 40 and 60 millimeters of mercury. Its characteristic is that the curve is steeper. A PO2 of 40 millimeters of mercury is equivalent to the PO2 in mixed venous blood. Hemoglobin oxygen saturation is about 75%, and the oxygen content is about 14.4 milliliters of oxygen per 100 milliliters of blood. This means that for every 100 milliliters of blood flowing through the tissues, 5 milliliters of oxygen is released. The percentage of the oxygen volume released as blood flows through the tissues relative to the arterial oxygen content is called the oxygen utilization coefficient. At rest, with a cardiac output of about 5 ml and an oxygen consumption of about 250 milliliters per minute, the oxygen utilization coefficient is about 25%. Different tissues and organs in the body have different oxygen utilization coefficients. This segment of the curve reflects the oxygen supply to the body at rest. The third segment is the lower part of the curve, the left portion, corresponding to hemoglobin oxygen saturation when PO2 is between 15 and 40 millimeters of mercury. Its characteristic is that it is the steepest. When tissue activity increases, e.g., during exercise, the tissue PO2 can drop to 15 millimeters of mercury. Oxyhemoglobin further dissociates, releasing oxygen. Hemoglobin oxygen saturation drops to an even lower level. The oxygen content is only about 4.4 milliliters of oxygen per 100 milliliters of blood. Thus, every 100 milliliters of blood can supply the tissues with 15 milliliters of oxygen. The oxygen utilization coefficient can increase to 75%, which is 3 times the value at rest. This shows that this segment reflects the reserve capacity of the blood's oxygen supply. The oxygen dissociation curve is not fixed. When the body's internal environment changes, the oxygen dissociation curve can also change. For example, shifting left or right. A shift in the position of the oxygen dissociation curve indicates a change in hemoglobin's affinity for oxygen. P50 is commonly used to represent hemoglobin's affinity for oxygen. P50 is the PO2 at which hemoglobin is 50% saturated, normally about 26.5 millimeters of mercury. When P50 increases, the oxygen dissociation curve shifts to the right. This indicates a decreased affinity of hemoglobin for oxygen. A higher PO2 is required to achieve 50% oxygen saturation. Conversely, when P50 decreases, the curve shifts to the left. This indicates an increased affinity of hemoglobin for oxygen. The PO2 required to achieve 50% hemoglobin oxygen saturation is lower. This is from the perspective of hemoglobin loading oxygen in the lungs. From the perspective of local tissues, at the same PO2, a right-shifted curve releases more oxygen than a left-shifted curve. This ensures adequate oxygen supply to the tissues. Therefore, various respiratory end products can cause the curve to shift right. For example, an increase in PCO2, a decrease in pH, an increase in temperature, an increase in 2,3-DPG, etc. Think about the changes in your body after running 100 meters. Doesn't this make it easier to understand and remember?